This lecture is to introduce students to the concept of percent composition. 60% of the time it works every time. That's a quote by Ron Burgundy from the movie Anchorman. So we want to be able to express things in terms of percent composition. And what that means is you should be able to represent the amount of an atom present in a compound. For example, if you have CO2 minus, or excuse me, CO2, you should be able to recognize that the carbon represents 1/3 of the number of atoms in the molecule. We also want you to be able to use percent composition by mass to obtain an empirical formula. And we also want you to be able to distinguish between what's called an empirical formula and a molecular formula. There's a big difference between those two that we need to talk about. So, the first thing we want to do is we want to look at what a molecular formula is. And what a molecular formula represents is it represents the number and type of each atom. So, for example, you have 4 carbons, 10 hydrogens, and 1 oxygen. Okay, what you should realize is that the molecular formula does not represent the connectivity of the molecule, just the number of each type of atom present in a given molecule. And you see that with these two structures that are shown below. So you see this one right here is C4H10O, but the oxygen is in the middle of the molecule. You see this one is C4H10O, with the oxygen and a hydrogen kind of off to the side. These two compounds both have the molecular formula C4H10O, and it does represent the number of atoms that are present of each type, but it doesn't represent necessarily everything that we need to know about the chemical or about the chemical makeup. So, if you have a compound such as C4H10O6, there's lots of ways that you can express the amount of each atom present. And the first thing is you can represent the number of atoms. For example, you can say there are 4 carbons. You can say there are 10 hydrogens. And you can say that there are 6 oxygens. You can also say that carbon represents 4 out of 20 of the molecule. Hydrogen represents 4 out of 10 out of 20 of the molecule. And oxygen equals 6 out of 20 of the molecule. But those things don't really represent anything of any given importance. Really, what we want to focus on is the idea of the percent mass. So, you see what we talked about here. You see there are 6 atoms out of a total of 20, or 30% of the molecule, or 30% of the atoms are oxygen. Okay? Doesn't really mean anything though, so we want to get something a little bit better, and that is percent composition by mass. In order to do percent composition by mass, what you have to do is you have to find the mass of each constituent part. So for example, there are 4 carbons. Carbon has an atomic mass of 12, so I multiply 12 times 4 and I get 48. 1 times 10, because you have 10 hydrogens. 6 times 16, you get 96 oxygens. That means that the total mass of this particular molecule is 154 grams per mole. So if I want to find the percent by mass of each particular compound, I just take whatever the mass of carbon is, divide it by the total, multiply by 100, and I get 31.17%. Or I can take 10, which was hydrogen, divide by 154, multiply by 100%, and I get 6.49. And so on and so on. The key thing though is it should add up to 100% because you have the whole molecule and you're trying to figure out what the percent by mass of each piece is, but overall it has to add up to the total molecule. So this is one of those things that you should be able to do. It's relatively straightforward, but you do need some practice with it. So let's give you an example, and this is a pretty tough example. It's got kind of a lot going on. It says thiamine C12H17Cl N4OS is one of 4 nucleotides that stores genetic information in deoxyribonucleic acid. So you knew it as DNA last year, and you said that there was A, T, G, and C. And that's true. This is the T, and the T is represented by this formula right here. A lot of people think, oh, it's T, it's just one atom. It's not. It's a combination of them. It's very complicated. So it says, what is the percent composition of each element in thiamine? So in order to figure out what we need to know here, the first thing we need to know is we need to find the total mass of the molecule. So the first thing that you should do is you should look up the atomic masses. And how you do that is you go once again to our periodic table. and you look at our periodic table, and we can find the atomic mass of carbon, we can find the atomic mass of, nitrogen, oxygen, anything that's on that molecule you can find. So, for example, chlorine is 35.45 and oxygen is 15.999. So you can use those to help us figure out what the atomic or the overall mass of the molecule is. So we start off with carbon because it's first. We say we have 12.011 atomic mass units, and we have 12 of them. So that right there is 144.132. Okay, so carbon is taken care of. Next, we look at hydrogen. Hydrogen is 17, and the atomic mass of hydrogen is 1.008. Multiply that out, and you get 17.136. Next, you have chlorine, and you have one chlorine at 35.45. So that is 35.45. You have four nitrogens. So you have 4 at 14.007 or 56.028. Next, we have one oxygen at 15.9994. When you multiply that out, you get 300.805. And then finally, you have one sulfur at 32.06. 32.06. Whoops, made a mistake here. This right here should have been 15.9994. You guys were probably wondering where I got that from. Now, when you take all of these things and add them together, what you're going to get is you're going to get the atomic mass of thiamine. And the atomic mass of thiamine, when you add all those things together, is 300.805 grams per mole. That's where that 300 number came from. So now you've got this 300.805 number. What that represents is that is the total mass of the molecule. So if I want to try and find the percentage that each molecule contributes, what I can do is I would divide each one by that 300.805, and I want to do that all the way down. When I divide each one by 300.805 and I multiply it by 100 to turn it into a percent, I get the percent of each molecule. And what you get is for carbon, it's 47.92%. For hydrogen, it's 5.70%. Go ahead and put the elements out there. For chlorine, it is 11.79%. For nitrogen, it is 0.63% nitrogen. For oxygen, it is 5.32% for oxygen. And for sulfur, it is 10.66%. Now, if you were to take all these percentages and add them up, you're not going to get to 100. And the reason why is we rounded at several steps. We rounded right here, and we rounded right here when we divided. It should be pretty close, though. It should be something like 99 to 101%. And if that's the case, then we know we just rounded and we have small errors due to rounding. But like I said, this is as tough as it gets because you have so many different molecules that you're trying to keep track of. Most of the ones that you do are going to be much, much easier than this when we do percent composition. So, an example of the next one, it says, what is the percent composition by mass of oxygen in barium sulfate? So one of the things that you have to know in order to start to solve this question is you have to know what the formula is for barium sulfate. And the formula for barium sulfate is BaSO4. Okay, both barium, which is 2 plus, and sulfur, which is 2 minus, balance each other out. So you have barium sulfate. So now, what is the percent composition of mass of oxygen? And so you have to figure out what the total mass is. So you start off with the idea of barium. You have one barium, and barium has an atomic mass of 137.327. And once again, the reason why I got that number is I came here to the periodic table and I looked at barium, And barium is down here, it's element 56, and it is 137.327. So we come back here, we have one barium at 1 times 137.327. We have one sulfur at 32.06, and we have 4 oxygens at 15.999, and we can multiply those out. And when you do that, you get an atomic mass of 137.327, atomic mass of 32.06, and an atomic mass of 63.996. When you add all those up, what you'll do is you'll get the atomic mass, or the formula mass, for barium sulfate. In this case, the atomic mass of barium sulfate is 233.353 grams per mole. So that represents the mass of 1 mole of barium sulfate molecules. So now what I can do is I can find the percent composition of each. And in order to do that, we divide each piece by 233.353. When you do that all the way down and multiply by 100, it'll give you the percent by mass of each particular compound. But in this case, I'm only interested in oxygen. So oxygen, 63.996 divided by 233.353 equals, you would get a value of 27.41% oxygen. Okay, so once again, you've got to find the total mass of the molecule. Once you have the total mass of the molecule, you divide the total mass of the whatever you're looking for. So the total mass of oxygen divided by the total mass of the molecule. One thing that gets people tripped up is they say, well, oxygen is 16, I'll take 16 and divide it by that. No, it doesn't work that way because you have 4 oxygens. So, another example that we have is, what is the percent composition of sodium in sodium sulfide? So you need to know what this is. Sodium sulfide is NaS, but this is a charge of +1, and this is a charge of -2. So the actual formula is Na2S. Okay, that right there is the balanced chemical formula for this. So next what we need to do is we need to say, okay, what is the percent composition of sodium in this? So I have 2 sodiums, and sodium is 22 point, I think it's 22.989, but let's take a look. 22.989. Okay, so 22.989. And then you have sulfur, which is 32.06. So when you multiply that out, you're going to end up getting something along the lines of, should be somewhere close to 46. Okay, we can usually round whenever we're doing these because you don't have to take it quite out that far. And this usually is something around the lines of 32. So when you find the total mass of these particular molecules, a single sodium sulfide molecule has a mass of 78 grams per mole. So if I want to know what the percent composition of sodium is, okay, I have to take 46 and I have to divide it by that 78 number. When you take 46 and you divide it by 78, and then you can't forget to multiply it by 100, you end up getting a percent of about 58.97%, which means the rest of it, the sulfur, has to make up the rest of it. It should be something like 41.02%. Percent composition is particularly useful whenever we look at something called combustion analysis. So one of the things that we do in science is when we don't understand something, what we tend to do is we tend to break it up, burn it, destroy it, convert it to something else, slam it together into something, and see what pieces fall out. And that's what we do when we're talking about combustion analysis. Basically what we do is we take some sort of sample and we burn it. And whenever we burn it down as far as we can, and then this vapor right here goes through these tubes. And the tubes actually consist of 2 different parts. There's a part that absorbs water, and you can find the mass of this before, and the mass of it after, and whatever the change in mass is lets you know how much water was produced by the reaction. And then you have something that's called the carbon dioxide absorber. And it does the same thing. The carbon dioxide comes through, is trapped. You can find the change in mass that's there, and you can figure out the carbon dioxide that's present. So using these two things, this carbon dioxide and this water, you can turn around and figure out exactly what it was that you burned. It's something called combustion analysis, and it's one of the biggest tools that people have whenever we're trying to figure out what certain compounds are, especially hydrocarbons, which are things like gasoline or natural gas or something along those lines. So, combustion analysis requires that you have this formula C6.6, and what you do is it's somehow converted into a combination of carbon dioxide and water. So what you can do is you can use the percent composition, you can use these formulas, how much carbon, how much oxygen, how much hydrogen are present that you figured out from here, and you can go back and retroactively determine what these numbers are. It could be something like C2, H10O1, it could be, or it could be any number of a number of other things. So the question is how do you go from percent composition to the formula that it actually was? And here's what you do. Number one, you convert all the percentages to mass and you assume there's a 100-gram sample. So in other words, 31.17% becomes 31.17 grams of carbon. 6.49% becomes 6.49 grams of hydrogen. You're just taking the percent sign and you're replacing it with a gram sign. You also have to make sure that the element that goes with it is there as well. So once you've done that, now you need to figure out the number of moles that are present in your sample. So you take the gram formula mass. Okay, so it's another one of those things where you look at the periodic table, you find carbon, you see carbon is 12, and when you see carbon is 12, or hydrogen is 1, or oxygen is 16, then you can use that gram formula mass to figure out the number of moles. Now, generally speaking, you do not have to take it out to 12.011 or 1.00794 for hydrogen. You can just leave it as it is at 12 or 1 or 16. Everything else will kind of work its way out, as you'll see in just a second. So, if I had a 100-gram sample like we talked about before, that would contain 2.5975 moles of carbon, 6.49 moles of hydrogen, 3.89625 moles of oxygen. And to tell you the truth, that doesn't really make a whole lot of sense. It doesn't actually give us any useful information. So what we need to do is we need to say, okay, it's clearly not this. The reason why is you can't have a part of a molecule. It has to be carbon 2 or it has to be carbon 3. It cannot be carbon 2.59725 because you can't cut a carbon into that many pieces, or any pieces at all for that matter. So what we do is we find the lowest number of moles. Okay, if you look, the lowest number of moles that we had before, was 2.5975. So I take all the values and I divide it by 2.5975, and as a result, what I get is 1 carbon, I get roughly 2.5 hydrogens, and I get roughly 1.5 oxygens. So that right there is getting close to an empirical formula. But I still have this problem. It's still not going to be CH 2.5 O 1.5. So now what I need to do is I need to multiply all the numbers by the smallest value that will result in whole numbers. And if you look, this 2.4985 is roughly 2.85. Remember, we didn't use the exact gram formula mass. This oxygen is roughly 1.5. So when you multiply it out, you get 2, 5, and 3. So then the formula for whatever it was based on that percent composition is C2H5O3, and it's finally done. Now this is one of those procedures that takes a little bit of time, and you need to be able to say, yeah, it's at 1.5. Is it close enough to 1.5 to count it as 1.5, or do I need to do something else with it? That's one of those things that it takes some practice. You need to make sure that you do some things with this. But now we have a problem. Based on this particular formula, I got C2H5O3, but I was originally told that the compound was C4H10O6. So I've got a discrepancy here. Okay? If you look, these are two clearly different compounds. One has 4 carbons, one has 2, one has 10 hydrogens, one has 5, one has 6 oxygens, one has 3. But if you were to take a look at these, they have the same percent composition. Okay, they represent the same percentage of the molecules. And that's one of the biggest problems with percent composition is it can just tell you the ratio between the atoms. It can say that for every 5 hydrogens, there are 2 carbons. It doesn't let you know necessarily that there are 10 hydrogens and 4 carbons, or 15 hydrogens and 6 carbons, and so on and so on and so on. So you need an additional information if you want to figure out what it actually is. Now this right here, the lowest common denominator thing, is called the empirical formula. The empirical formula The empirical formula is the simplest whole number ratio of atoms in a molecule. For example, if you took a look at this is what I originally had. That's not the simplest combination of atoms. I could take all of those and divide by 2 and get C2H5O3. That right there represents the simplest combination because if I were to divide by 2, I would get CH2.5O 1.5, and you can't have half of an atom. So because of that, this right here is what we call the empirical formula. And the percent composition, whenever we do those calculations, can only tell you the empirical formula. It cannot tell you the molecular formula. So because of that, you need to be careful about what you say as a result of your percent composition equations. So, working backwards, combustion is just one type of reaction. There's lots of other ones that you can do in terms of percent composition, but regardless, if you're given the percent composition, you use the exact same process that we used with combustion. Okay, if you have any sort of percent composition data, you should be able to derive the empirical formula from that percent composition. Now let's look at a couple of examples. The first one says a sample is combusted in the data shown below. You have 40% carbon, you have 6.67% hydrogen, and you have 53.3% oxygen. So we need to go ahead and figure out what the empirical formula is based on that. Now eventually we want to get the molecular formula, but we'll talk about that in just a minute. So the first thing that we need to do is realize that these are not percentages. These are grams. Okay? Then what we would do is we would divide each by the molecular formula or the molecular mass of each element. So carbon is 12, hydrogen is 1, and oxygen is 16. As a result of that, we will get the number of moles of each in the sample. So for this first one, we have 3.33 moles of carbon. We have 6.67 moles of hydrogen, and we have 3.33 moles of oxygen. So we have C 3.33, H 6.67, and O 3.33. Now what we need to do is we need to divide by the smallest number that's there. The smallest number is 3.33. So we divide all these numbers by 3.33. And as a result, we get carbon, there's 1, hydrogen, there's 2, and oxygen, there's 1. Now remember, what that represents is that represents the empirical formula. But remember, I'm trying to solve for the molecular formula. In order to do that, I need another piece of information. I need it from somewhere. So there's lots of other places the information can come from. You can be given another data set, another test, something indicating how many carbons there are. And in fact, in this case, it says that further analysis shows the sample to have 6 carbons. Well, if there are 6 carbons, you need to multiply carbon times 6. But you need to do that for each molecule, or each atom in the molecule. So as a result, this is actually C6H12O6, which you learned about in biology as glucose. Next, it says a student is attempting to ascertain the identity of a sample based on the information below. It says you have sodium, that's 32.17%, hydrogen, which is 1.4, phosphorus, which is 21.68, and oxygen, which is 44.75. So remember, the procedure is to say that these are all grams now, not percent, and to divide them by the molecular mass. So I would go to my periodic table, and I would make sure I knew what the molecular mass for sodium is. Remember, sodium is element 11, and it says 22.989, which is roughly 23. So we'll say divided by 23. Hydrogen is 1, phosphorus is 31, and oxygen is 16. When you divide that out, you end up with 1.4 moles of sodium. You end up with 1.4 moles of hydrogen. You end up with 0.7 moles of phosphorus, and you end up with 2.80 moles of oxygen. So you identify the smallest number, which is phosphorus. You divide each one by 0.7, and when you do, you end up with 2 sodiums, 2 hydrogens, 1 phosphorus, and 4 oxygens. So that is our molecule, Na2H2PO4. The last example that we have, very similar again, says what is necessary to have a combustion reaction and what does it produce? One of the things that you need to know is that a combustion reaction is generally taking something like C6.6, H, Y, O, Z, where X, Y, and Z can be any numbers, including 0. So, for example, you can combust something like CH4, even though there's no oxygen. The Z value is just 0. You can combust something like H2O, okay, because you have just the C or the X value is 0. But in this particular case, you have to have something like that, and you have to have oxygen present. Okay, that's the requirement. If there's no oxygen, something will not burn. You can actually make a fire, you can control the temperature of a fire by increasing the oxygen flow or decreasing the oxygen flow. And in this particular case, the more oxygen you put in, the more it will burn. Okay, as a result of mixing these two things, you will produce some combination of carbon dioxide and water. Now, the carbon here must come from the carbon there. The hydrogen here must come from the hydrogen here. Now the oxygen's a little bit different because the oxygen can come from either the molecule or what it's burning. So that's where it gets a little bit trickier in terms of trying to balance out the equation, which we will talk about in the next unit.